So my name is Brad Urani. I work at Procore in Santa Barbara, California. We make construction management software. This is a talk about relational databases. And the reason I chose this talk is I really wanted to give a database talk. I looked into a lot of like really modern cutting edge databases that I wanted to talk about, but I thought it would be a little disingenuous to come up here and talk about some new cutting edge, new SQL kind of functional database or whatever, because I don't actually use any of that stuff. Like most of the world, I build products for a living, and so I'm forced to use sort of like, the boring old tech, our old SQL databases. But I happen to think that's okay because I really like this technology. Somehow I think it's the most, despite being the workhorse of sort of the software development world, relational databases somehow managed to be underappreciated. And so I wanted to sort of give a fresh look at this, just a little appreciation over why I think they're so neat, why they're still great tech, and why you might think twice before using anything else. So the whole relational concept was invented by this man, Edgar Codd, in the 1970s. He wrote this great paper. He had this wonderful idea for a better way to make a database using all this relational theory, a database that would be faster and much better than the things that existed. He was working for IBM at the time, and the thing is, IBM already had a database. It was a non-relational database. It was old tech, and even though everyone knew this would be a lot better, the database they had was selling really, really, really well, and they didn't want to make something better because they didn't want to cannibalize the sales of their own products, which means this man was the first man to actually take these ideas and bring it to market. That's Larry Ellison, if you don't know. His SDL later became a company called Oracle, which you might have heard of. And IBM's probably kicking themselves pretty hard because he's now the world's 7th richest man, having taken their idea and made all the money off of it, and now he makes bombastic statements such as, "I invented the cloud." And no, you didn't, Larry, be quiet, you're obnoxious. Okay, so fast forward just a little bit to the 1990s, we have open source databases came into the works. Believe it or not, if you think about this, if it was 1994 and you were an indie developer, there was no open source database you could use. You had to shell out big bucks for IBM or Oracle. Imagine that. These are the early internet days, right? And there's not actually a relational database you can use if you don't pay for it. So this was a big deal in the software development world when this came along. But things got a little funky when this company came along called Google, and they wanted to make a web search engine. Well, all of a sudden, the relational databases at the time couldn't quite satisfy the requirements of what Google needed. You see, all these years, we had Moore's Law, and computers got faster and faster and faster, and the data workloads that people had to process got bigger and bigger and bigger, kind of in lockstep. And so that as you got bigger and bigger, faster and faster machines with bigger and bigger processors, the relational database could continue to do the job. But Google hit this so-called web scale. Well, all of a sudden, their data processing workloads were so massive that they actually outstripped Moore's Law and needed to do something different. So it used to be like this. Can we throw more hardware at this problem? Yes. Next slide. But that was in the old days, and Google proved that doesn't work. They had to do something different. They had to make a distributed database. So if your data is huge, you had to shard it. You have to put it on more than one node because it couldn't fit on one machine. And since this is the internet, now we're global, now we're worldwide. We also had to worry about how far away the data is. This is not, a single on-premise solution. So we had to go from a world of scaling up to a world of scaling out, which required something different. Now here comes this NoSQL thing, right? This is about 2005 now, and all of these different new exotic solutions come off that are loosely based on some of Google's ideas. And what do they give up? Well, it's this. This is what a database is founded on. ACID. These are the guarantees that a database gives you. So what NoSQL did is it did away with a lot of these guarantees, but there's something important you have to realize there. Is if you're thinking about these databases, and you think about, NoSQL and all these new, awesome new solutions are, just newer tech, that's not really the case. The only reason they're faster is they give up a lot of these guarantees. So it's actually a stripped down database with fewer features. That's the only reason they get the speed out of it. I think that could be misunderstood. I think a lot of people, when they were looking at this, the whole NoSQL phenomenon, thought that somehow this was just some more advanced solution and people thought of a clever way to do stuff, which is why they made this faster database, and that's not true. They just gave fewer guarantees, fewer features. So now the world's changing yet again, and all of a sudden SQL is back in vogue, and once again it was Google who said, you know what? We invented NoSQL, we invented the post-SQL world, and guess what? There's a big drawback to that type of thing, all those guarantees. Turns out we want those. Turns out that makes life easier because our developers now, they can't rely on database for transactional support and those things. They're just implementing that and re-implementing it at the app level, and we'd rather have them developing features, things that the users see, rather than re-implementing what the database used to do. So let's go back to this world. Let's just figure out how to make it distributed. And they have, and they won't tell anyone how it works. So some new databases have come out here and tried to figure out what it is based on their F1 paper. None of them, in my opinion, are quite ready to be used. But in the meantime, what's great is that Moore's Law has continued, and it's still going and still chugging away. And so now, these old relational databases like Postgres and MySQL, just because of Moore's Law, all of a sudden, they can handle most of your web-scale loads, which maybe they couldn't back in 2005. They're a lot faster now because computers are a lot faster, and all of a sudden, maybe you don't need all that NoSQL stuff to begin with. Which brought this joke, you've probably seen this one, 1970, there was NoSQL. In 1980s, you had to know SQL. In 2000, no SQL. In 2005, it's not only SQL, and now it's back to no SQL. Okay. But I think there's another interesting phenomenon that went along about the same time, which is there were certain groups of developers that were looking at these databases like Mongo and Redis, and were using them despite not having any scaling challenges, despite scale not being an issue. Why were they doing that? The way I see it, they might disagree with me, I think there was somewhat of an aesthetic consideration there, because you take something like Redis, it's a key value store, it's real simple to imagine how it works. You know, you've got a key, and you've got a binary tree, and you go straight to the record, and it's one algorithm, and it's all of us easy to conceptualize. I think people really liked that they could hold these ideas in their head and understand how they worked clearly without a lot of magic, and so they gravitated towards these solutions. But I think that's too bad because they were giving up features that they didn't have to give up. And so one of my hopes with this talk is by making the internals of how a relational database works a little more familiar, to maybe sort of move away from those aesthetic considerations and appreciate that it's, for most cases, the relational database is a better solution. So NoSQL hipsters, don't be a NoSQL hipster. You know, think carefully before you don't go with the obvious choice here. Okay, and yeah, guess what? We have the cloud now, so you know, it's web scale. So what does this have to do with FP? Well, you know, it's not a very functional solution, right? A relational database it has mutatable data. It's not immutable. Really, the relationship here is if you're a software developer, if you write in a functional programming language, you're basically stuck with SQL anyway, so you're probably going to use it. But there are some similarities, right? SQL is very declarative. It does not have like mutable variables. You can use it in a way that's persistent. There's a pattern called event sourcing, where you basically don't delete or update anything. You just kind of record a transaction log and then aggregate things up, which gives you all the sort of functional style immutable properties that you want. So it just depends on how you use it. But what I'm really interested too is how the way this works can inform the next generation of code design, which I'm going to talk about in a bit. So when I run a SQL query, here's what happens. I've got it goes through 4 steps. First, the parser, then the rewriter, the optimizer, and the executor. So the parser is going to say, all right, here's my query. Select star from users. First, is this valid? Do these tables exist? Do these fields exist? You know, are the operations possible? Is the user authorized? So it's going to start by just basically validating this is a valid query. It's going to then it hands this off to the rewriter. The rewriter basically makes up for your own mistakes. So you might have written an inefficient query, and the rewriter's going to go, all right, convert these views to a SQL statement. If you've got extra nested subqueries, we're going to flatten those. If you've got extra operators, for instance, if you're pulling back from a column with a unique constraint, but you've got a distinct on it, then it's redundant. You don't need that, so we'll take it out. We have extra operators and stuff like this. So what's happening here is the database is starting to figure out how it's going to run your query. And that's the big difference between a query language and a programming language, is that in a programming language, we're very much still in the world where you're telling the computer exactly what to do. You know, if you go in Haskell and you write a bunch of list operations and things like that, you know, that's always going to execute the same way. This is different because you're giving it a rough set of ideas. I want this table joined to this one, joined to this one. And there's an extra step in there where you've got this whole query planning process where it's going to figure out the optimal algorithm. And I'm really interested to see if this kind of stuff can translate back to program runtimes. The future will see. So this query optimizer it's got a lot of information to work with, right? Before it runs your query, it's going to say, how much CPU do I have? You know, disk I/O, how much memory? The disk I/O is really the important one, by the way. What indexes exist? It takes all this information, and this is called statistics. So every database, what it does is it keeps statistics about your table. So it might say it knows the number of rows, it might know the distribution of data, it might know the average size in each field, it has a histogram and memory of like the distributions of like the size of your fields and stuff like that. So it's going to gather all this kind of information, and then it's going to start plugging in algorithms, and it's going to choose its algorithms for you, which is where the genius part of this lies. So let's just look at a few of these. Most of these are pretty simple. First is a B+ tree. Okay, does everyone know how a binary tree works? That one's pretty simple, right? B+ tree is a little different because what a binary tree can't do very well is ranges. So say I've got a binary tree and I want to look up, okay, give me record 10, right? You recurse through that tree and it finds record 10, fine. What if you want to say I want to find 10 through 15? You'd have to traverse the whole tree, which isn't efficient. So B+ tree fixes that by having an efficient way of doing ranges. In a B+ tree, the only values that are actually part of our data set are the bottom row, the orange ones. So the green ones there are these placeholder values. They're not actually part of the data set. It's 15, 40, 67, 99. That's my data. What happens is the leaf nodes in the tree have a link to the node that comes after. So for instance, if I want to find everything between 40 and 99, I traverse the tree, 65, 25 down there to 40, and then I've got immediate rows that I can immediately just shoot to the right and collect things, and that's how you do an efficient range. This is what happens when you add an index on a column in a database. So in a database, right, the rows are written out on disk in a table format. So if you don't have an index and you say, okay, give me number 40, it just starts at the top and goes right down the bottom and it finds 40. That's not very fast. It's checking every row to see, is this it, is this it, is this it, is this it? When you create an index, it creates this tree sort of on disk next to your table and uses that to look up the rows, right? So then you get much faster look at performance. The downside, of course, is now you have to maintain this tree, so when you're writing to the database, not only do you have to write the row, you also have to insert a node in the tree. So more work on the inserts and updates, but much faster to read from. So time complexity challenge, you all saw that algorithm. You all know this, if you've ever done like a chalkboard interview or whatever, this is to help your job searching skills, right? What's the runtime of that? Anyone want to guess? What's the runtime of a binary search? Log n, right? So it's log n, and it's log n if you're looking for one node. If you're looking for a range, it's log n plus m. M is, so if you're going from 95 to 100, that's 5 things, so m is 5. So it's m plus log n. If you're looking for 5 elements in a range, it would be 5 plus log n. Okay. So let's look at a merge sort. This is what a database uses to merge to sort data. And really the reason I'm going to show you this one, because you probably all know this, is because it helps you understand the merge join, which is coming later. This is a divide and conquer algorithm. It's got a low RAM footprint. It's the opposite of good FP practices. It modifies arrays in place, right? This is not persistent data structures because it has to be fast. It's low I/O, data can be partially loaded to RAM, it's parallelizable. And why do I show you this? It's to realize that, you know, when you think of like your computer science education, you learn the runtimes of these algorithms. Oh, this one's big O of log n, this is big O of n. But there are more considerations in a database because what's really more important than sort of that runtime speed and stuff like that is how it utilizes the resources on the box, right? So like, if I've got a whole lot of RAM, you know, I can use a different algorithm where if I've got limited RAM but high throughput on the disk, and the query planner is going to take all that stuff into consideration before it picks an algorithm. So this is a pretty simple algorithm. It's divide and conquer. So we start with that list, 8654. We recursively split it down into individual elements. Then we merge it back together. So we take adjacent elements and we order them from 4 down to groups of 2 down to 1. Just basically merging things back together as we take this thing we split apart and recursively recombining it again. Okay, in Clojure it looks like this. I love Clojure for like its sort of just simplicity here. So we can see the recursive calls in there to merge sort. There's our recursive algorithm, and then that function MRG is the one that actually does the merging. So that looks like this. I realize that this is kind of a lot of blobs on screen. By the way, all the algorithms I had like Clojure examples for, but I realized that throwing these up on screen, like most people don't sit there like actually, so I took most of them out actually, and I think the talk is better for that reason. So anyway, what's the complexity of that then? Come on, someone else. A merge sort? And log in. There you go. Ding, ding, ding. You get the job. Can you do it on a whiteboard? Okay. All right, so let's look at joins. So the first type, when we're joining things now, I'm going to show you 3 joins. And just like I said, the query planner in the database is going to decide which join algorithm based on the resources on the box, based on how much you can read into RAM, how much throughput it has in disk I/O, what the bottlenecks of the systems are. So here are some actual titles from LambdaConf talks that I've actually taken from the real schedule. Monads for better nachos, understanding Sesame Street with applicative functors. So a nested loop join is exactly what it sounds like. It starts with the table on the left, and for each one of those, it loops through the ones on the right, so you get basic nested loops. It basically tries every combination of things to try to join these things together. Okay, what's the complexity of that? Nested loops. Someone yell it out. That one's going to be n times n. So if you've got n records on the left and m on the right, it's going to be n times n, isn't it? So, but really, like I said, what really matters are the constraints on the system. So the next one, alternatively, we could do a hash join. So the way the hash join works is it's going to look at, what I'm joining here is I'm joining on speaker ID. So I'm joining the talk to the speaker. So first thing it's going to do is it's going to take the table on the right and create a hash table, and it's a bucketed hash table. Databases use very, very simple hashing algorithms. It might just be something like, index modulo 10 or something like that, which is not guaranteed to create unique values, which is why you end up with buckets. So the reason it doesn't do that is because imagine for a second you wanted to use MD5 as your hashing algorithm. That's really expensive. And all the performance gains you get by negating are negated by the fact that you have to run MD5 on everything. So it uses a really simple hashing algorithm that creates buckets. So it may take 1,000,000 rows in your table and just modulo 100,000 or something and have a bunch of buckets with 100,000 buckets with 10 items each in it. It's basically what it does. So it's going to create that hash table on the right, and then all it really needs to do then is start on the left, take the speaker ID, hash it, find the representing bucket, and join it together. So it's incurring the cost of creating a hash table out of the right side relation, so that when it runs the algorithm, it can match them up faster. So a little, a little investment in the beginning, leading to a faster algorithm in the end. Time complexity of that. Anyone want to try to figure that out? Okay, assuming you've already created the hash table, right? Because there's expense in creating the hash table. Then all you have to do is take the ones on the left and find the corresponding ones on the right, and the time complexity of a lookup in a hash table is big O of 1, right? So in this case, it's actually, wait, let me get this right, I don't want to mess this up. I think it's big O of m plus n, because you're, for each one on the left, you have one on the right. So, yeah. Okay, so, and one slight variation to that is if you can also, the databases sometimes will decide it might be faster, based on the heuristics it has, it might be faster to create hash tables out of both sides so that you can just match bucket to bucket at that point. So that's a minor variation on that. All right, so now let's look at merge join. So merge join takes 2 lists and it basically just kind of says, all right, here's the one and here's the other, and let's just sort of like interleave these. Let's just sort of co-link these in a way where we preserve the order. But what do you need in order to do that? Well, realize the lists have to be sorted to start with, don't they? Those lists are already sorted. We're just merging 2 lists that are already sorted together. So this is a very fast algorithm if you're starting with 2 lists that are already sorted. And what's the complexity of that? Anyone want to guess? That would be big O of, oh man, I forgot, m log n, I think. Okay, so, all right, what's interesting is that when you run, like, so if you run, what's interesting is you can see the database doing this. So I'm showing you all these things, but realize you have visibility into this process. So if you use a relational database, something like Postgres, it has this method called explain analyze, where it'll give you the plan it uses in the query. So this is an actual one from an actual query that's running in an actual production app. There you can see that I wrote a join and it decided to use a hash join. In this case, it could have used a merge join, it could have used nested loop joins, but for whatever reason, the query planner in its brilliance figured out that this would be the fastest in this case. And knowing this can help you figure out, if you study this and you get into it, you have to optimize queries. Knowing that that's what it did will help you write better queries, and if one's going slow, it'll help you figure out how to fix it. Also notice it did a quick sort in there. The one I showed you was a merge sort. This one did a quick sort. Why did it choose a quick sort this time, not a merge sort? Probably the amount of RAM. Quick sort is faster than a merge sort, but uses more RAM. At this point, the query planner probably went, ooh, you know what? This box isn't very busy. We've got a lot of memory. Let's go for fast. Let's go for quick sort, more RAM, faster result, because I can. So the most interesting part, though, is not just these simple algorithms. It's how the query planner goes and decides which ones to use. So, and what might be sort of like this process? Well, we're doing this join. Is one table bigger than the other? If that's the case, if you've got a small table on the left, actually, no, I take that back. If you've got a smaller table on the right, like we've got a table with a lot of rows on the left and just a few rows on the right, a nested loop join might be very, very fast. It might be the fastest choice. If the tables are closer to equal size, it won't. It might try to do a merge join. That's especially true if it's, a merge join is the one where, for it to do a merge, both sides have to already be sorted, right? That would be the case if both those tables have an index on them. So it might say, ooh, this has an index, this has an index, these are sorted, we can do merge join, that's the fastest one of all. If they're not sorted, but your query ends in an order by, meaning you want the results back sorted, it might say, you know what, the fastest way to do this is to first sort both sides, then do the merge join and get back a sorted result because that's what you wanted anyway. Lots of duplicates, a hash join would be fast, but not if the data is skewed. So the database is going to use heuristics to figure out which of the ones it thinks is the fastest. How much time do we have?
3 minutes.
3 minutes, okay. So what we have here is the join ordering problem. So here's a simple query with 3 joins. I've got foo, join to bar, join to baz, join to bonk. So the database is going to look at this and go, ooh, how do I want to execute this query? Well, I've got a few options. I could join foo to bar, and then I can take that result and join it to baz, and I can take that result and join it to boink. Or I could join baz to boink, and take that and join it to bar, and take that and join it to foo. Or I could do foo to bar and baz to boink and join the 2 together. All end up with the same result, but with different performance. And it's got these other choices. Each of those joins, which one should they be? A hash join, a merge join, a left and loop join, a nested loop join. I've got the database has to make a choice. So the first thing it's going to decide is brute force or greedy. What it's going to do is evaluate all the potential query plans. So it's going to do its best to pick the right one. If there's not a whole lot of choices, like if there's only one join, if it's a simple query, it might exhaustively try every combination of that, running heuristics to try to make a guess at how long a certain query plan will take before it runs the query. Sometimes, though, there's so many options that it has to use a greedy algorithm to try to figure that out. My favorite, the most complex, being the genetic algorithm. This is an algorithm that mimics natural selection, and it's a greedy method for finding the best guess of what the best query plan is. So it works like this. You're going to start with just like a plan, it's just going to pick a plan at random. Then it's going to mutate that and make like 10, 50, whatever, 100 variations, slightly different variations. Then for each of those variations, it's going to say, all right, what is my best guess about how long this will take to execute? All right, let's take the top 10% of those, ditch most of the slower performing ones, and then start over and take those and mutate and make 100 variations off those. So it does this sort of like wash, rinse, repeat thing where it mutates, finds the best, ditches the rest, mutates, find the best, ditches the rest. So for instance, it might start, with just a random guess. I'm just going to start here and say, this is my best query plan. All right, now I'm going to swap these 2 nodes. So I've swapped bar with foo. Now I'm going to take my best guess and see how long this one takes. Is it better? Oh, good. Then I'll keep it around, and I'll just try to mutate that one next time. Also, it might randomly mutate the types of joins. So hash join, hash join, hash join. I think that'll take X milliseconds, but this one might be a little faster. So it's going to wash, rinse, repeat, and find what it thinks is the best query plan using a genetic algorithm. Caching, I can skip. So relational and functional world. I guess the questions I come up with at the end of the day when I look at functional programming and relational databases, what is the state of functional databases? It's not that great, which is why I'm talking about relational databases too. It's still the best thing we have. Was NoSQL a flash in the pan? I don't know. That's up to you all. Will NoSQL be the new standard? I hope so. And what can programming languages learn from SQL databases? What I'm really interested in is you look at that declarative syntax, which is something we value in the functional programming world, which SQL does really well. SQL is even more declarative than, for instance, Haskell. Can we take some of these ideas from these query planners and build them into programming runtimes and make our languages ever and ever more declarative? Is that possible? I don't really know, but I hope someone figures that out. A few resources up here. I'll tweak these slides. My name is Urani. Follow me on Twitter. Connect with me on LinkedIn if you want. I've got a blog that I seldomly update. I work in Santa Barbara at Procore. We make it construction technology software. It's a great place to work. That's the view from my office. We are hiring. We got a lot of Ruby. We've got a fully functional React-based JavaScript front end. We're adding microservices and Elixir Phoenix and Rust. So we got some cool technologies, and I'd love to talk to you if you're interested.